All these clips is for the analysis of statically indeterminate structure. We are going to use the force method to analysis. What is mean by statically indeterminate structure? The structure we are going to talking about is going to be the beams, the frames, and the truss. The structure going to be statically indeterminate. That means it cannot solve by using only the equation of equilibrium. For example, if we have the pressure of a building and the beam of the pressure is a kind of cantilever beam like this, and if this one subjected to the force of 10 kilonewton, and this is going to be 2 meter and 2 meter, and you can use usually the free body diagram of this 10 kilonewton 2 meter. You can find the reaction at the fixed support of this beam easily. It's going to have like a sub y, a sub x, and it also has the moment of m sub a here. If you do the summation of x sub x equal to 0, you will get a sub x equal to 0. And if you do the summation of f sub y equal to 0, you may get the up is positive. So your a sub y is going to be 10 kilonewton. And the last one, if you take the moment at a here, you may get summation of m sub a equal to 0. So if you have this one is the positive, so m sub a gonna be 10 times 2, that is 20 kilonewton meter. Okay, and you can draw the shear diagram, you can draw the moment diagram, and you also can draft the elastic curve of this beam. And since this beam is fixed only one side and free on the other end, this beam may have very large deformation. Okay, under the application of this one, you can use your ruler and push the force at the middle of the ruler. You can see this part of this beam gonna curve. Okay, and this part of the beam is a straight line. And sometimes the pressure of your building maybe get very large deformation. You can fix this by adding more support into that portion of the pressure. For example, again, you have the pressure like this. The force still the same, 10 kilonewton. However, this time you may add up the support at the free end. Okay, and then you may put the column, okay, to taking care of this. So your beam now is going to have what? It's going to have more reaction. Typically, this beam, if you draw its free body diagram, the reaction at A is going to be the same. It's going to have what? The A sub x, okay, the A sub y, and the moment m sub a here. That's due to what? Due to the 10 kilonewton, okay, and apply at 2 meter here. But now, since you pop up, okay, you pop up B by this column. So this portion of the beam will have one more reaction. Let's call this one is B sub y. Now, the unknown, okay, the unknowns of this problem is going to be 4. Your equation of equilibrium still be there, 1, 2, and 3. So equation of equilibrium gonna be 3. So this beam gonna have what so-called the degree of indeterminacy, or you may call it DOI, equal to 4 minus 3 equal to 1. Okay, and to solve this, that means you're gonna need one more condition to solve it, and this is the extra force. Okay, so we will introduce the concept of the redundant force, and we set this one as the unknown. Okay, by solving the unknown of force, we call the analysis of this kind of structure the force method, and we're going to use again the equation of equilibrium as before. However, you need more condition of the compatibility. We need the compatibility, okay, of the beam to help to solve this. And also, you also need to have the force and displacement relationship to help to solve this kind of problem. So the analysis of statically indeterminate structure gonna be a little bit harder than the statically determinate structure that we usually study this kind of statically determinate structures in engineering statics. And we're going to study a lot of statically indeterminate structure in the structural analysis, the next course from here. Okay, the learning objective. In this chapter, the first, I will introduce you the advantage, okay, and also the disadvantage of the statically determinate and indeterminate structure. Most of them have positive and negative side. Okay, for the determinate, you can analyze it easily, but the determinate may have large deformation. Okay, and statically indeterminate, you're going to build more support, so the cost of construction may be get bigger. And the second, this is very important part that you be understand and be able to analyze the statically indeterminate structure by using the force method. That means you're going to study about the beam, the first part, the frame, and the truss. Okay, by the method of consistent deformation and the method of least work, and we will focus a lot on the consistent deformation. Okay, the homework. Since you study three kind of structure, so the homework will involve the beams, these two one, the frames, and the truss here. You have going to have 5 homework. Okay, so the basic of the definition of this statically definition of this. The statically indeterminate structure is structure that has stability. That means is stable, it won't move under the application of the loading. Okay, and the total unknown of the reaction and the internal forces and moment is larger the total number of equation of equilibrium of the structure. Let us consider the bridge over here. There is a bridge. Okay, the bridge is built on the pier, and let's say if we assume this is the pin, this is the roller, and this is the roller. Okay, this is show you the support here as the roller. What do we have for the reaction for this portion of the bridge? Okay, you may have for sure is let me put it in black, or reaction here Okay, let's say it's AS of y. It also have AS of x. It also have BS of y. It also has Cs of y. So we're going to have the total of what? Of four unknown, four unknowns reactions, which is what? Which is larger than the equation of equilibrium, larger than equation of equilibrium, which is 3. And this kind of stuck of beam, also called the statically indeterminate, with the degree of indeterminacy equal to 4 minus 3 or equal to 1. So you can solve this beam by using the force method, by setting up one redundant force. And you solve for the redundant force, you can analyze the structure completely. This slide shows you the cast-in faces Landforce concrete frame. Usually when you build this one, after you finish building the foundation of this, you may start by putting the reinforcement, and then you put the formwork, and then you cast the concrete into the column. You cast the concrete into the column. You do the same thing. You cast the concrete. You may do simultaneously, or you may do separately, whatsoever is up to the procedure you use in your construction. You're going to study that in the construction management. Okay, you're going to talking about how to construct the structure in the construction management. You may plan how to build it, and then you build all of your column. Okay, after you finish the column, you will cast the beam to link the column, okay, together. And what you have the rigid joint. Okay, you have the joint. And oh, sorry, that is the wrong writing. Let me take this one out. J-O-I-N-T, the joint, J-O-I-N-T, that's rigid joints. Okay, and you have this one is the fixed support. Okay, so the structure is going to be very rigid. We call this kind of structure as the rigid frame. Okay, this is a kind of very stiff structure, and when you do the model of this, it's going to be 1, 2, 3, 4, 5, 6, 7. That is 1 bay, 2 bay, 3 bay, 4, 5, 6, and 7 bay. And then you cast the beam to link all the column together, and now you have the fixed support. And what you have when you analyze this kind of structure under the force, let's say this force may act on the structure, such as the wind load may apply here, and you also may have the uniformly distributed load that's act on the roof of your structure. And then what you have is how do you draw the free body diagram of this. And if you consider, since the supports are fixed, so each of them gonna have 3, 3, 3, 3, and 3 unknown forces. That is going to be vertical force, horizontal force, and the moment. Each of the supports going to have 3. So the total unknown of this unknown of this is going to be unknown reactions. It's going to equal to 3 times 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be 3 times 8. That is 24. And since the structure connected together, and you may consider it as the one free body diagram. So you have one free body diagram, and one free body diagram gonna have 3 equations. So you have the number of equation of 3, and then you have the degree of freedom of what? So sorry, degree of intimacy of what? DOI equal to 24 minus 3. That is going to be 21. That means if you like to analyze this structure, you're going to have the total of 21 unknown forces to solve it. Okay. And if you go back to your chapter 3, this kind of frame, you also can calculate the degree of indeterminacy by just cut this one. 1, this is 3, 3, 3, 3, 3, this one also 3, and this one also 3. This one also equal to the total of plus, also equal to 21 degree of indeterminacy. Okay, the RC Landforce's concrete frame is usually the statically indeterminate structure, since the structural members are constructed as a cast in place and they connected continuously. Next, we come to the bridge. Not only the building, the bridge also. Okay, when we talking about the bridge, we have this one as its foundation. Okay, this is foundation, and then we have the rigid frame. This one, the whole thing of this. Okay, we may call this as a rigid frame. During the construction, okay, the contractor will start by building the pile and casting the foundation to cap the pile here, and then they construct. They may place the reinforcement and the formwork, okay, and cast the concrete into this column, and two of them supposed to build simultaneously, okay, up until here, and then you build a cross beam. This may call the cross beam, CROSS is the cross beam. After finish the cross beam, you build another portion of the column, okay, and all of them going to get according to schedule that you plan basis on what you study of this construction management course, okay, and then you build the top of your cross beam. Okay, this part of structure you may call it substructure of the bridge. Substructure of the bridge. Okay, and during the construction of this substructure in the factory, you may have the precast, pre-stressed concrete beam, okay, BEAM, produced in the factory, and at the same time when the substructure finish, the precast pre-stressed concrete beam will ship to the construction site, and you may use the crane to put the precast pre-stressed concrete beam into its position. Okay, after you finish putting this one, you can cast the floor. Okay, you can cast the floor and the other thing into this structure. This part of bridge, we call it the superstructure of the bridge. Okay, and the beam can be considered as the statically determinate beam. Okay, the beam it depends on how you construct it, and when you analyze it, decide it, construct it, everything gonna align in the same way. Okay, coming back to our structure. So now you have the structure of this bridge. The substructure gonna be like this. What is going to be the degree of indeterminacy of this bridge? Okay, by doing this substructure have two stories. Okay, by using the same method as before. On the top, Okay, you may just cut the frame. When you cut the frame, each cut going to produce 3 and 3. So this is going to have degree of indeterminacy of 6, as you know before. Okay, if you don't want to, you may use the classical procedure. This also have 3, this also have 3. So your frame, okay, gonna have one of this and another one of this. So the unknown reaction, okay, the unknown reaction gonna be 3 times 4. That is gonna be 12. And the free body diagram that you have is 2, and you have 3 equations for the free body diagram. So your known equation gonna be 6, and finally your degree of indeterminacy gonna be 12 minus 6, and then it's also 6, as you may know. Okay, that is a kind of analysis of this kind of structure, and this should provide you the insight of the difference between the statically determinate that's built on the superstructure beam and also the frame. Okay, the frame gonna be kind of a rigid frame that is gonna take a lot of force. Okay, maybe the force from the wind, from the hurricane, from the earthquake. It's up to you. It's up to the area that you are design this structure. Next, coming to the steel frame. Okay, the steel frame, this bridge, pedestrian bridge across the road, built by a kind of rigid frame, as we just mentioned before. Ajahn, this is supposed to be the truss. No, this is the rigid frame if you consider it. Okay, for the truss, this frame is supposed to have the diagonal member. If this one is the truss, okay, the truss will different from here. The truss will have diagonal and horizontal member with this one, okay, to transfer the force across the structure. And for the truss, the support is gonna be pin joints, okay, pin joint. And for the truss, what else you got to have? The force gonna apply at the joints of the truss. That is the truss. It's different from the structure above here. The structure above here, there is no diagonal. So the joint, okay, that link the beam and the column together on this structure must be rigid joint. It's not a pin joint, it must be rigid joint. That means it will take the axial load. Okay, it also take the shear, and it also can be take the moment. So each joint of this gonna have 3 equations of equilibrium, unlike the joints of the truss that we have only 2 equations of equilibrium. That's different. Okay, so when you design, you're going to build the rigid frame pedestrian bridge. Okay, you're going to do the model. Okay, your model gonna follow with the rigid joints, and your joints gonna be rigid joints when you're constructing. You got to be very careful on this. Okay, and the model of this bridge also different from this one. And again, for the building, the same thing as the bridge. Okay, the joints we consider every joint is supposed to be the rigid joints, and you got to do the detail of this by follow what you plan to do so. Okay, that is the basic. You got to understand the difference between the statically determinate structure. This one, the task is going to be statically determinate task. Okay, but over there is going to be statically indeterminate frame. Okay, that is going to be different thing. And the advantage and disadvantage. Let us consider the beam. Okay, our beam have the total span of L, and is subjected to the force of P. Okay, at the middle of it. And what happened is, you can analyze this beam. This is statically determinate beam. Okay, you can analyze this beam by using the equation of equilibrium. Then you have the reaction of P over 2, and you can draw the shear diagram like this. The maximum shear gonna be P over 2, and you also can draw this is S equal to 0. This is slope equal to 0. You also draw the moment diagram here, which the slope here is gonna be P over 2. Slope here is minus P over 2. And you have the moment here is 0, and moment here is 0, since this one is the roller and this one is the pin. And under the application of this force P, you can determine the maximum deflection that occur at the middle midspan, the middle length of the beam. And the same thing, if the same force apply to the beam with the same span, and this time we have the support change from the pin to the fix of both ends. Now this structure change to statically indeterminate structure. Actually, it also have the A sub x, but it's equal to 0, and also B sub x is equal to 0, since this beam have no horizontal force. And due to the same force applied to this structure of P, okay, you can calculate that. Okay, the reaction here is going to be P over 2. So the shear diagram of this beam and the previous one is going to be the same, and the maximum shear going to be Vmax equal to P over 2. That's it. It's going to be equal to Vmax. However, since this beam will has the moment occur at the support due to it is fixed, so the shear diagram of this beam is changed. Okay, and you can see that previously the maximum shear is PL over 4. Now, due to the fixed end, the moment distribute from the middle to the midspan to the fixed support, and the maximum moment change for P over 4 to PL over 4 to PL over 2. So the statically indeterminate beam, this beam has only half of the moment compared to this one. Now, what we have is, when we do the design, we set sigma allow equal to M max times Y over I. Okay, and we call this as the S. It's going to be M max divided by S, and S is going to be, go back to mechanics of material, also called the section modulus. Okay, so when the M max changes by a half, you decide this for the S required is going to be M max divided by sigma allowed. Since this one is fixed and this one reduced by half, so the S here, okay, the S here, the required S for this case is going to be a half of S1 here. Okay, so the section of this beam will have a smaller section modulus by a half. Okay, then it has smaller moment, then we have the smaller section. Okay, if we provide again, we're going to have this one. That means you're going to have smaller section. Okay, next, for the deflection, if we provide the beam with the same I, okay, we provide the same I and the same S. That means if you provide the beam with the section modulus, that means the beam you can count on the same I. And when you consider this beam is fixed. Okay, since this one is fixed, when it's subjected to the force, you may represent it by putting the ruler and put the force at the middle and hold the both end fixed. You will get the elastic curve of this. And the same thing, if you just release this as the pin and allow the rotation of this as a roller, so the theta here is not zero. The theta here is not zero, but the theta here is zero and theta here is zero. So the maximum deflection from this will reduce. And if you consider the coefficient here and here, this is going to be what? 48 times 4 is going to be 192. That means this beam, if you set equal I, okay, if you set equal I, is going to have 4 times less deflection. Okay, with deflection. That is the advantage of the statically indeterminate beam. In short, okay, if you design the beam based on the bending moment, you will get the smaller section. Okay, if the beam have the same equal I, the deflection going to be less. And then the next one, we come to this one, and this one also talking about the distribution of the stress. Coming to this one, the moment diagram of the statically determinate have zero at both ends, but for the fixed support, due to the fixed effects, both ends, the moment at both ends will redistribute from the middle to the support. And if you combine them together, I mean, combine this one, this is going to be PL over 8. This is going to be PL over 8. The total going to be PL over 4, which is equal to here. And the effect of this is called the internal stress distribution that occur due to the support, okay, that help the beam to resist the internal moment better than the pin and better than the roller. Okay, and next, the bad effects due to the redistribution of the stress when the structure have some kind of settlement. You know settlement of the building foundation, right? That occur in the S9 dormitory. That's my dormitory. Or now the settlement of this also occur as the C building. We are fixing this building now. You may come and take a look at this. And the crack, okay, we redistribute between the middle of the beam and the support. Okay, that is the bad thing about the stress redistribution. The third advantage, the statically determinate structure originate the cantilever construction. Okay, if you're building very large bridge across the river, you are going to build the support of your bridge under it, under here. That's going to be very big job. Okay, instead of this, engineers going to build this portion of the bridge and support it, okay, stiffly, okay, at this two end. And now if you draw the model, okay, your model gonna be fixed here, and also you have the fix here, so you can build this cantilever portion of the bridge, okay, and the support here and here gonna help to take care of the portion that you build. On the other side, the same thing. If you also build it and then you support it, okay, with strong one, and also put this one, you may build the portion of this, and it's going to cantilever out of this. In this portion, you also can do the construction, and it's going to cantilever like this, and then it's going to connect together later. And this is going to be very good effect, because if you have the lever across here, okay, it's going to be very hard job for you to set up all of the formwork to support this kind of construction. That's going to be very big problem to build this kind of formwork, okay, formwork to support the bridge segment is very hard. Okay, so cantilever method help you to construct this bridge without the formwork like that. Or it's also, if you have the boat, okay, that's going to use this lever during the construction, okay, without this formwork, the boat can move, okay, across the area that you construct this bridge easily. That's also be convenient for the transportation. And you may change from this lever, you may change to a kind of highway, okay, it's the same thing. It's really convenient if this one have the load that's the vehicle can move past it during the construction, or if the lever, the boat can move past it during the construction. Another example is India. This is clearer picture. You may see they built two parts of the bridge and join together. But you got to be very aware of the construction, or you must be very aware of the precision of the construction. I mean, to make this one reach it at the middle span, you got to be very careful on this. And when you join this, it's going to be very delicate work, okay, and that is depend on the construction technique, okay, NIQUE that you use to link them together. The disadvantage, since the statically indeterminate structure require very fixed support, so the detail of the construction of this should take the moment, okay, not only take the typical shear and the normal force. It's going to take the moment. So the detail of the support of this structure going to be more complicated than the pin support. Okay, the fixed support gonna use more complicated. So the structure you design and you analyze may be more complicated. The detail of this thing also must be very careful when you trying to to do the detail of this thing. And next thing, the construction cost of the support. Okay, gonna be putting more complex bolt into this part, and it's gonna need a lot of construction. But for the reinforced concrete beam, okay, these joints will be automatically linked together by using the reinforcement and the casting of the concrete. The differential settlement of the foundation, if you have the beam, okay, with the fixed support as before, you may demonstrate this easily by your hold your ruler very stiffly, and then you move one of your hand, okay, downward, and what you see is the beam gonna change its shape to something like this. This one what would occur if you have, okay, just pick up the ruler loosely, and then you move one of your hand downward here, and you may see your structure can change the shape easily without bending. Okay, since they can move without bending like this, so there is no shear, no normal force, and no moment. But by doing this thing, there is going to be the moment occur here. For example, the moment here gonna have the direction here, and it's also may have the shear force due to the moment. It's also the shear force. So this one also have the, if you take moment here, this moment here, you're going to have the shear here. If you have downward shear here, you're going to have the upward shear here. So the settlement of the foundation of the statically determinate structure gonna produce internal moment and internal forces acting on the structure. So you got to prevent the settlement to the statically determinate structure. This also, if you want, is going to produce crack, okay, on your structure. This also occur in some building at SUT, because when we built our university, we come during the summer. When we come during the summer, what we have is what is the soil in this site is really steep. Okay, so when you investigate that soil, the soil going to have large strength, and then you design the building based on that. So what happened is you would need to have the pile into the foundation, and what occurs is when you use the building for quite a while, what happened is the water coming into your foundation, and that's produce the settlement of the foundation. So you got to fix it, and over here we fix the problem by using many methods. Okay, one of them we use the micropile. You may search it by using the goggle, okay, to fix the settlement, of the building foundation. There are many methods to do so, but one very effective is the macroPie here. For the statically determinate beam, such as cantilever, overhanging beam, or beam with internal hinge, they can move, okay, according to the settlement of their foundation. No internal forces and moment to the structure, but the function of structure may be good. The function of structure going to be bad because the increment of the structure. Anyway, you also gonna need to fix this kind of problem. Next, we have the problem with temperature change. If you go back to your mechanics of material, chapter 4, okay, and when your structure supported by the fixed support, and then the temperature change, maybe due to the sunlight, what happened is this portion trying to move, okay, try to expand, and the support won't let it move, so it's going to produce the stress inside this. If the change of temperature is large, the stress is going to be also very large, okay, as you may know on that. So that is the main advantage of this structure. Another one, this is a picture that shows the crack due to the settlement of the S9 dormitory in SUT. And the other one is talking about the levers, okay, the stress reversal. There is the stress reversal occur in the statically indeterminate structure. For example, here the structure connect to each pass by the support. So when the structure subjected to this force here, this portion AB gonna move downward, but the portion BC has no force, so it's gonna move upward. And then if the load just change the size to the BC, the deflection of the shape, the different shape of the beam going in the opposite direction. And you're going to be very aware of this, because if you have this kind of problem, what you're going to do is you're going to reinforce the structure is in different way. For this one, you may put the reinforcement at the bottom. This one, you put the reinforcement on the top, okay, but this one you put the reinforcement on the top, and this one you put reinforcement in the bottom, so they are in the opposite. So the analysis of design of structure must consider this stress reversal during the analysis and design. And method of analysis, and we are going back to mechanics of material, and you may recall there is two ways to analyze this. It's called force method, okay, which going to use the force as the unknown, Another one we call displacement method. This one we going to use displacement method. Sorry on this. Just take this one. This one going to use the displacement, okay, as unknown. They are different. Let us first consider this one, and you may have this weight. Let's see, has the 10 kilonewton. You may draw the free body diagram of this one. This is going to be the X, this is going to be the Y, and this is going to be the 10 kilonewton. And what we have is we has the force, this one F sub AD along this cable, and also have F sub AB, okay, along this cable, and you also has the direction of this. It's going to be 3 4, and it's going to be 4 3, and you can solve this by using two equation of equilibrium. Okay, this based on the method of choice. You can determine two unknowns from the two equation of equilibrium. However, when you come to this one, this problem has 3 cable. So under the 10 kilonewton force, what we has is this gonna have 3, 1, 2, and 3 unknown. It's gonna be F sub AB, F sub AC, and F sub AD. Now, you have only two equations. Okay, you know the direction of this. You have only two equations. We have 3 unknown. Okay, we have 3 unknown with 2 equations. So we cannot solve. This one is example of statically determinate and statically indeterminate for very basic structure. And what else? For this kind of structure, you may need more, okay, more equation to solve it. You're going to have additional consideration of this structure by consider the compatibility condition. That means you're going to consider how this structure gonna change, okay, under the application of the force, for sure. This one, okay, going to have some kind of deflection. So the deflection of this structure going to come to play in this analysis. We call it compatibility condition. And since the deflection is based on the force, so we also need the force displacement relationship over here. Okay, that means you need to go back to chapter 7 to determine the displacement of the structure. Okay, that's why we finish our displacement first, and we come to this portion on after we finish that. Okay, let us review the displacement method for this structure. This is the axial load structure, statically indeterminate axially loaded column. Okay, under the P, this one gonna have the reaction. Okay, this is gonna be F sub B, this is gonna be F sub A per se. And since the force is axially loaded, that means it's passing through the centroid of the section. So the summation F sub X is 0. That's correct. And also you have summation of moment equal to 0. Also correct. And then you have the other one equation left is summation of F sub Y equal to 0. So we get this equation. F sub A plus F sub B upward and minus P equal to 0. This called statically indeterminate with degree of indeterminacy equal to 1. We need to have the condition that help in this analysis is called the compatibility condition and called the force displacement relationship. Okay, so the compatibility condition. Under the application of the force, what we have for sure is this structure. If you consider this one, okay, you draw this portion of this column. They may have also to consider the portion of this column, and what you have is this portion subjected to the reaction F sub B, and this portion subject to the F sub A, and the same thing. If you do the summation, the internal force here is F sub A, and internal force here is F sub B, but they are different. This one gonna be what? This one gonna be in tension. So this portion gonna be elongate. Now is have elongation. This one going to have compression. So this one gonna have the contraction. Okay. By this, when it occur, you may take rubber band, you hold it with your left hand and right hand, and ask your friend to pull in the middle. What you have is the consideration of the deformation of this one. So this portion gonna move to here. Okay, and this is gonna move from C to C palm, and this portion gonna shorten, okay, to here. And what we have is the displacement between A and B have no change. So no matter this is gonna be elongate for the portion AC, or it's going to be contraction for the portion CB, the length between A and B have no change. So we can write like this. Okay. But for this one, what we have is change from C to C palm. So this one you may ask like the displacement of C with respect to A is in elongation, and this one is going to be minus the displacement with respect to B, okay, C with respect to B, and two of them when combined together it's going to be 0. So that's going to be what's so-called the compatibility condition. This compatibility condition based upon the consideration of deformation of the structure. Okay, so consider the deformation of the structure. So we have the compatibility condition. The structure is supposed to compatible to each other. Okay, based on this. Next, you're going to use the force displacement relationship to link it. Now, we have what? This is going to be the structure that is going to be have the stress equal to F over A. Okay, and this structure have some kind of deformation delta. Okay, so we have the strain equal to delta over L. And what we have is sigma equal to E epsilon. So this is going to be based on the Hooke's law. Okay, so we put this one is F over A equal to modulus of elasticity, the deformation over L. Now equation is going to be here. Okay, so in the analysis of statically indeterminate structure, you have equation of equilibrium, you have the compatibility condition, you have the force displacement relationship, 3 of them. And now each of them you just consider it. Okay, for this free body diagram as I draw it, the delta C slash A. Let's say the delta C slash A is going to be based on this one, or basis on this one together. So the F is going to be F sub A. Okay, the L going to be L sub AC and divided by AE. Okay, and another portion is going to be this one. The F is going to be F sub B. The L is going to be L sub CB. Since the column have the same area A, this one is the area. Okay, is the area A, and the same modulus of elasticity. Okay, this one gonna cut, and then you arrange this equation, you get the solution for the F sub A. So this one and this one, you have two equations. This one you may like it like F sub A equal to this one equal to this one is F sub B, and before that you may have this one of L sub CB divided by L sub AC. Okay, you put this one F sub A into, sorry, you may leave it. Okay, anyway, you may put this one into this, and then you solve for F sub B, and you get F sub B here. After you get F sub B, you can get F sub A here, or the levers whatsoever you like, and then you obtain the reaction. And since the reaction is positive, so what you assume direction of the reaction is R. They have F sub A and F sub B are correct. This is called the displacement method. You may see first we draw the free body diagram. Okay, and we use the equation of equilibrium, and then we use the compatibility condition, and then we use the force displacement method. Next, for the force method, again we have the axial reloaded structure as before, and then for this one again we have this one of F sub A and this one of F sub B, and all of the force are aligned passing to the centroid of the section. And what we consider is this one have 1 degree of indeterminacy, and the degree of indeterminacy gonna be the unknown force. So it's up to you. You may use the F sub A, or you may use the F sub B to be the unknown force, and we call this unknown force as the redundant force. That means we have more force, redundant, more force, and you determine you're going to use F sub A or you're going to use F sub B. It depends. Okay, if you use F sub B, so your structure will change to this. Okay, the structure will subjected to P and F sub B in this case. And now you may use the principle of superposition. You may use the principle of superposition. Now we separate the the column into two portions. Okay, one is subjected to the load P. We call this is primary column or primary structure, and this gonna plus the one that's subjected to the redundant force. Okay, so we use the principle of superposition to separate this. The fourth method, you consider the structure, you consider the unknown reaction, and then you can see the unknown reaction is more than the equation of equilibrium. So you decide which one is going to be the redundant force. And when you decide which one is the redundant force, this one you take F sub B. So you took F sub B. So you draw the structure into separate structure. One subjected to the applied force, another one subjected to the redundant force. And then what you have is you're going to start by consider the compatibility condition. What you have is this one under the force is going to have the deformation of delta P. And you can calculate the delta P by using the equation of what as before, delta equal to FL over AE. And we have this before. This is what? This is going to be the force displacement relationship. So the force method start by compatibility condition. Okay, the displacement method start by the equation of equilibrium. And now the force P. Okay, move this one downward. F sub B, move this one is upward. So the downward, you got power is positive. So what we have, this one is 0, equal to delta P is here, okay, plus this one is delta B, and since delta P and delta B have opposite direction, so we have the negative side here. Okay, and this is going to be elongation. This is so-called elongation. This is going to be contraction. The problem is we don't know this directly of F sub B, right? So the problem is we are going to find the F sub B, in which is going to be the redundant of this column. And next, just taking care of the force displacement relationship. The first one, we determine the delta P. Okay, if you cut this portion, there is no force. If you cut this portion, okay, it's subjected to the force P here, and what we have is going to have the force here of what? Of P, and it's going to occur in this length between A and C. So it's going to be P L sub AC divided by AE. Okay, and then this one, if you draw this one, you may see this is going to be F sub B, and the internal force also be F sub B. And if you cut the other portion, the internal force is going to be F sub B. So it's going to be F sub B times L divided by AE. And then you put this one back into the equation. And then you may have this one cut and cut. And then you get F sub B here. When you get F sub B here, now you're going to use the equation of equilibrium to find the F sub A. Okay, so you may conclude that the displacement start by equation of equilibrium. Okay, and then you use the compatibility condition, and then you use the force displacement relationship. But for this one, you start by the compatibility. You use the force displacement relationship, and then you use the equation of equilibrium. You get both F sub A and F sub B. Okay, and in conclusion, you may say the force method, okay, use force as the unknown. When call this is the redundant than, okay, maybe force on moment also, that is going to be redundant, is more than necessary. And then we first use the compatibility, and then we use the displacement, and then the third we use the equation of equilibrium. Okay, and for the displacement method, we will study it in structural analysis. Okay, and it can be the methods such as slope deflection, okay, method, or the matrix displacement method. Okay, we're going to take this in the next subject. For the displacement method, we use the displacement as the unknown, and then we first use this, and then second we use the compatibility condition. Okay, and third we use the force displacement relationship to solve the problem. Okay, and anyway, you use the force method or you use the displacement method, you require to use the principle of superposition to separate the structure into many cases. It's up to the problem you are consider. Okay, and this principle of superposition bases on two assumptions. First, under the force, the material behave linear, elastic. Okay, and this is follow what we study. If you have the beam subjected to uniformly distributed load W, you may have this one, and this one is going to be linearly proportion to each other. That means if you have this one for 10 kilonewton per meter and this one is 10 millimeter, and you increase this one to 15 millimeter, sorry 15 kilonewton per meter, this one gonna up to 15 millimeter. You may check on this. It's linear relationship. Okay, and what it means is under the application of this force, what we consider is only in this portion of the behavior. Okay, we didn't consider this portion, and if this one is sigma sub y, we also use this one as the sigma sub y divided by factor of safety, which we use this one as the sigma allowable. So usually our civil engineering structure is linear elastic, and since it's linear elastic, most of the time it's going to have very small deformation. In the design of the beam, we limit our V allowable to be L over 360 if the beam has the wall underkit, or L over 240 if there is no beam underkit. Okay, there are a lot of things that you got to go back and check. Okay, this is going to be the beam. Okay, this is going to be the deflection equation. Okay, and this is going to be the deflection equation with respect to x, equation with respect to x. Okay, to x. This is the deflection equation for given x, and then you may use this equation to help you to determine the structure. This is for the simple beam or simply supported beam. This is for cantilever beam. Okay, and you got to be very careful using this equation, because this equation and this equation will come from the equation on the right hand side of this table. Okay, now come to the method of consistent deformation for the beam. We will start by the most basic one. We have the cantilever beam, and then we have a support, additional support at B. And what we have is when we put this one into position, we will have this one as the unknown B sub y. This one may have A sub x, and this one A sub y, and this one going to be M sub A. So we going to have degree of indeterminacy equal to 4, and then minus the equation of equilibrium time one free body diagram. So this one will be 1. Since this one is a consistent deformation based on the force method, okay, we are going to have this one as the linear force of this problem. So we're going to have 1. We're going to have 1 linear force for the beam with 1 degree of indeterminacy. Okay, so now we change this one to this one. Okay, and if we like to change this one to this one, we need to go back to the basic that we just mentioned before. This is going to be based on the principle of superposition. Okay, and now the beam subjected to type of force. One is going to be the applied force. This is going to be the applied loading. Okay, and another one subjected to the linear force. So we're going to separate this one into 2 more cases. Okay, by this one applied loading, and this one for the linear force. And the structure or the beam that's subjected to the applied force. Okay, this is changed from the statically indeterminate, changed to form statically indeterminate. Is changed to determinate, and then the beam changed to cantilever under the force of P, and it's going to plus, okay, the beam that's subject to the linear force. Under the application of this, so you use the previous knowledge that we have from the previous chapter. The elastic curve of this one, this portion going to be curve. This is going to be curve, and this one going to be the straight line. Okay, this one going to be curve, and another one is going to be the straight line. You may show or demonstrate this by using your ruler. Hold it at A. Okay, very stable, fixed, and then put the force as P. You may see the A and the P going to be curved, and from the P to the free end, it's going to have the straight line. This is free. Okay, and this is fixed. Okay, and what we have is for the linear force is going to push this curve up, delta palm sub BB. Since the B sub y is unknown, the delta palm sub BB also unknown. So practically, we just let B sub y equal to 1 and do the calculation. We calculate the deflection at B due to the applied force SB, and this is due to the 1 unit load. Okay, and when the load is B sub y, you just time this F sub BB by B sub y. So the compatibility condition is going to be what? 0. This is going to be 0. Okay, this is 0 equal to delta sub B. If delta sub B is downward, it's going to be positive. So 0 equal to delta sub B. And this one, delta palm sub BB is upward. So we have negative here. and then we redraw this one, okay, into this equation. This is going to be delta sub b minus b sub y, 0 equal to f sub b, and the first b is the point of the side deflection, and then the points of the application of the Landforce, the deflection at b due to the force at b, and then you get this, okay, put into this equation, and then you get this one, and the b sub y is over here. So next, you use the force deflection relationship, okay, to put into this compatibility condition to get the b sub y. And when you get the b sub y, you know the b sub y, you can determine the auxiliary actions, the shear diagram, moment diagram, and also the elastic curve. Okay, let's come to the first example that we have. This one, we have the beam with the constant EI, that means the fractional rigidity. Constant, okay, with the length of L, subject to the force P at it with the length as before, and we use the consistent deformation to analyze this. And by doing this, we mostly set b sub y as the redundant. Okay, we are going to solve for the unknown force. After we have all the reaction, we draw the shear diagram, moment diagram, and find the deflection at the loading point. So after we select b sub y as redundant, the structure can separate into two beams based on the principle of superposition. Okay, and as we have this structure, we will have the compatibility equation in this form. So the problem is to determine delta sub b and f sub bb. You may use the conjugate beam, you may use the method of virtual work, you may use the Castiglione theorem to determine them, or you may also use the table, the deflection table, to determine it. Okay, let us use the deflection table. So if you consider this one, compare which one? Okay, this one. The first one, we're going to determine the delta sub b. That seems like we're going to find the Vmax here. So the equation of this is going to be this equation, right? Okay. And the other one, we have f sub bb. We don't know the force b sub y yet. This one, the force applied at the end, just in this way, but it's just in opposite direction. So don't worry, the deflection, the magnitude of the deflection is going to be the same. So coming into this, just change this one to b sub y. So what we have is this equation, and also this equation, L cubed divided by 3 over EI. You put it into your equation, and then you get this one for 5p over 15. This is may pass another step. This one gonna be 5pl cubed over 48 EI. Then it's going to be divided by,นะครับ okay, this is going to be what? L cubed over 3 over EI. So this one cut, this one cut, L cubed cut, L cubed cut. So you get this one for 5p, no L, 5p divided by 5 times 3, sorry, 5 times 3, 5 times 3 is 15, and divided by 48. Okay, and then you divide them by 3. Actually this one gonna cut this one to 16 also, and then you get the result, and it's upward. Okay, now you get this, and actually you may have the a sub x. Okay, you summation of x sub x equal to 0, a sub x equal to 0. By doing this, you summation of f sub y equal to 0, so upward is positive. So this one is upward, right? So a sub y plus this one 5p over 16 plus 5p over 16, and it's going to equal to downward, equal to p. So a sub y equal to 16p divided by 16p minus 5p over 16. Not p, no p here, no p here. Okay, 16 divided 16p, that is 1. And this one gonna be equal to 11p over up. Okay, over 16. Okay, you got to have a sub y here. And then if you do the summation of the moment at a equal to 0, just take moment here and take this one as the positive. So your m sub a gonna up. Okay, and this one b sub y gonna time by l plus 5pl over 16, and it's going to be p time this one, p time l over 2. Okay, so m sub a equal to this one is going to be 8pl, okay, over 16, and minus 5pl over 16. So this is going to be 3pl over 16. That is going to be m sub a, as you see, and it's also have the a sub y. Now you ready to draw the shear diagram. You can do it easily. You have what? Upward here of 11p over 16, and w here is 0, so dv by dx is 0. And then you come to this point of p, so it's going to be minus p plus 16p, 11p divided by 16. So this one going to be minus 5p over 16. And then w is 0, so the dv by dx equal to 0. And then you get this one cross. How about this moment? To draw the moment diagram, this is going to be positive, or this is going to be negative. And if you use the sign convention of m, you may see it's rotate in the same direction. If you move to the right, that is going to be negative. So 3pl over 16 going to be negative. Okay, this is going to be negative. And then you have this one is going to be the dm by dx equal to 11p over 16. This is plus, and it's going to arrive here. How do you get this? M here minus 3pl over 16 moment here minus moment previously is going to be equal to this one, 11p over 16 times L over 2. So your M is going to be 11pl over 32. And this is plus minus 3pl over 16. This is 32. This is going to be changed to 6. And you have this one for 5pl over 32. Okay, it's going to be positive. and then the dm by dx equal to minus 5p over 16, and then you get this for 0. What else do we have? As here we have this one is the positive, and we have this one is negative. So this one have downward curve. This one is upward, concave downward. Okay, so this is gonna have some important point of zero moment. The zero moment going to provide the inflection point. So what we have from this is the elastic curve. Our curve gonna be like this. This is fixed. Okay, this is concave downward. This means this is concave downward, and other portion is concave upward. So this is going to be the elastic curve of this beam. Okay, and what else? Since the beam have this kind of shape, when you consider this, you're going to reinforce this beam upward. This one, and this one you're going to put this one in the lower portion. Okay, that means the reinforcement of this beam, if this beam is the RC beam, the main reinforcement going to be like this. Extra main reinforcement, the top, okay, and the bottom. And normally this beam have their own reinforcement already. Just put this one like this, and just put this one going like this. Okay, and you also may put some reinforcement for the shear stirrup. That is going to be more on this portion, because this portion has larger shear and maybe less or have a large spacing for this portion. Okay, that is going to be the shear deformation, if you like. And also, if you like, you may determine the position for this point. Like I said, this is inflection point. This is very important because it's the point that change the moment from positive to negative. Okay, and the point that we change the reinforcement for the negative on the top to positive on the bottom. And can we determine the distance x here? This is going to have what? The shear of 11p over 16. Okay, and you have this one for the moment of what? Of 3pl over 16. So if you summation of moment equal to 0 here, you have the moment here equal to moment here, plus 3pl over 16, 3pl over 16 going the same direction like this, and you have this equal to 11p over 16x, and then since the point moment equal to 0, and then this is 16 and 16 cuts, and the p cut. Now you may get x equal to 3l over 16, or 11, sorry, yeah, over 11. Okay, this is 3l over 11. Okay, that is going to be the point of inflection point. Okay, you will get this set the elastic curve. Okay, you can show in your PowerPoint if you like. And next, they ask us to determine the deflection as pointy. Okay, what we have is we're going to use the conjugate beam. Okay, when you use the conjugate beam, that means what? That means your beam gonna change. Okay, this one gonna be the same as before. This is gonna be B palm and fix, change to free. Okay, and then your elastic width gonna change. That is gonna be upward. That is gonna be downward. So this is going to be your conjugate beam, and then what you determine, this is D palm, right? So what you going to do is you're going to use this portion of this beam, D palm and B palm, to determine the M sub D palm. M sub D palm is going to be delta D. So before that, it is important for you to find this one first, B sub Y palm. So we start by to find B sub Y palm. And then if you know B sub Y palm, you may take the moment here, find M sub D palm. Okay, coming to this. Okay, on this we will find later. The redundant, if we change the moment at the redundant, as you may see, if we change the moment in the statically actual beam gonna change. If you change into the beam with M sub A, that means we need to take the fixed support and change it into pin. Okay, and you have the M sub A as the redundant force. So your beam gonna be something like this. Okay, and you change this one to hinge, you got this one as the M sub A. Okay, take this one out. Same thing, this is a pin, this is a roller. And now you can separate the beam into simple beam. One subject to the force P, another one subjected to the M sub A. Okay, and now what we have is we're going to set up the compatibility condition, but this time the compatibility condition is going to set at point A. What we have is this one gonna have theta equal to 0. Okay, because the moment reaction here prevent it from rotation. So the primary structure subject to force P, so this one gonna rotate for theta A, and this one subjected to redundant force. Okay, it's going to rotate it by alpha sub AA for M sub A equal to 1. Okay, when M sub A is the unknown, so just M sub A times alpha sub AA. Alpha at point A, due to the force applied at A. Okay, so now you set up, you make this one clockwise and positive. So this is 0 equal to, this is positive theta sub A, and this is positive theta palm sub AA, and theta sub palm of AA is going to be M sub A and alpha sub AA. Okay, you put this one This one is a point of design slope. This one point of linear moment. You get this. Okay, by setting up the moment m sub a equal to 1, you get this for alpha sub AA. And now the m sub a gonna be minus theta sub a divided by alpha sub AA. And then we use many methods to solve for the slope. And from the table, okay, we can solve for the theta sub a and for alpha sub AA easily. Okay, coming to this. This is the beam, the force P. Okay, we are going to find theta max. This one gonna be our theta sub A. Okay, and this one, if change 1 to 1, this one going to be the rotation. This one alpha at point A due to the moment applied at point A. So this one will be alpha sub AA when change this one to 1. Okay, so alpha sub AA is there. Sorry, theta sub A is there and alpha sub AA is clean. And then you put them together. PL square over 16 EI and 1 L divided by TEI. Okay, just cut this one. So M is going to be 3 PL over 16 as before. And then we just forget about negative here. So this is going to be negative. Okay, so this one is going to be 3 over 16 PL. This one, sorry, this one is incorrect direction. Okay, we got to change this one into this one. So for the previous one we set this, so this one gonna have the direction in opposite to this one. So we have m sub a in this direction. Forget about this. This is a little bit wrong in our PowerPoint. Okay, and then after this you can determine f sub a sub y, b sub y the same as before, and know the shear diagram and moment diagram, and also you may calculate the so-called the conjugate beam as I mentioned before. This is going to be B palm, this is going to be A palm, maybe C palm. Okay, this we also have this one before if you put it. Okay, and then you can determine the delta sub C. Go back to the previous slide, and then you're going to get this one. And downward, this is shoulder downward, negative. Okay, that's all we have for the first portion of the analysis of statically indeterminate structure. And then we come to focus on the beam. Okay, and that's supposed to be the first portion, and then we have more examples to discuss later in the second portion. Okay, that's it.